My name is Christian. I'm from Intel. I'm a software architect involved in data plane development kit. Wrote a few components from the start of the project years and years and years ago. And I have a few personal involvements into this project, a few babies that I put into this project. So today I think I have two sessions that are back to back. One on an overview of DPDK, another one on optimizations, just get a bit into describing the optimizations, the software optimizations that we do. So I kind of presented these things for a number of times to different people. You tell me if you need to drill more into things, if you have questions, or we need to skip some of these things if you know them already. It's a pleasure now to talk about DPDK. Actually, it was mentioned in the last number of days a lot. So at this point, probably everybody knows that DPDK is actually sits at the foundation of VPP. It provides the Polmo drivers for getting packets in and sending packets out from the system. It provides the infrastructure for setting up some of these resources, setting up the system, and hopefully other things, other cool components from DPDK will also make it into a VPP. There is some kind of overlap in terms of functionality, like there are libraries that you might see, or concepts, or let's say functions that you might see implemented in both places, in DPDK as well as in VPP. So hopefully over time we'll just converge towards single implementations for some of these things. That is because, as Damian said, the VPP project started a long while ago, maybe even earlier than DPDK started. So there is a lot of legacy code from Cisco. We started with the code basically from scratch in DPDK. So sometimes you get several implementations for the same thing, but that should not be an issue. It should be just an opportunity to improve. So a pleasure to talk about DPDK. It's an open source project, well known at this point, a very successful data plane packet processing project. Major contributors you see over there. So I'm sure you probably, guys, most of you are already getting emails from the dpdk.org mail list. Is anybody here who's not using DPDK? Okay. Didn't see that.
Here, but I have to.
Okay.
Doesn't mean I want to.
Okay. Yeah. So okay, we'll see what we can do about it. You seem to be the exception, so it's good actually. So yeah, we can talk about why that is. So a lot of companies there. You can see a long list of contributors. We have users, but we also have contributors who actively develop and patches that are included into DPDK. You can see on the left-hand side some statistics about number of contributors, number of commits. I'm sure that Vincent and Thomas will also present you more numbers about DPDK and how successful the project is in the next during the next presentations. You can see like a long list and of like companies from different fields. Is not just, let's say, chip vendors. We also have equipment manufacturers and other folks over there. DPDK, although it started with Intel in mind, it was originated by Intel, right? And it was initially implemented for Intel CPUs and Intel NICs. Nowadays, it's actually multi-architecture, multi-CPU architecture, and it also provides support for NICs from different vendors. So here is a quick roadmap of DPDK releases and how we added support for different CPU architectures along the way, how we added support for different NICs along the way. So nowadays we have Intel, but we also have ARM, we also have power architecture, and we also have tile architecture. In terms of NICs, we have Intel NICs, but we also have Mellanox, we have Cisco eNICs, we have Chelsea or Broadcom NICs, Netronome NICs. Yeah, so nowadays DPDK is the place to be, and most of the NICs are already there, so you don't need to go and search for them elsewhere. This is a quick map of various components that we have in DPDK. So what exactly is DPDK? It was mentioned before as well. It's a set of libraries for improving the performance and functionality of data plane products, packet processing products for various applications, right? It's not just for one particular application, it's for a lot of applications, a wide range of applications across the board. So we can look at all these components, like you can see, like a lot of libraries over there. We also have, by the way, sample applications, examples to show you how to use those libraries. VPP, you can say it's one of the big users of DPDK. It's not a sample application, of course, it's a stack. It's an application with a stack. It's a very complex system. That also incorporates DPDK and okay, maybe it's not the code to start looking into. If you just want to start with DPDK, you should probably not look into how VPP is using DPDK. It's probably not the easiest starting point, but for example, I'm doing this as well. I'm also looking and ramping up on the VPP code and trying to understand how DPDK is used over there, how Polmo drivers are used, how the various threads, as Damian presented today, there are a number of thread combinations in VPP, and they all look and use DPDK in slightly different way, and that's also evolving. So on the left-hand side, you can see like a number of components that we call core components, core libraries. For example, EAL, Environment Abstraction Layer. That's one of the components that also VPP is using, maybe not entirely, maybe with some changes. What it does, it actually sets up the system for you. As DPDK is in user space, we don't have to do a lot of, we basically leverage all the hard work that Linux kernel did. So what is EAL doing? For example, it helps with the CPU enumeration or identification. We need to understand how many CPU cores we have, how many hyperthreads we have, how they are mapped to different CPU sockets, right? Do we have one CPU socket or do we have 2 or 4 CPU sockets? How are they connected together? So obviously that is straightforward. We don't need to rely on BIOS. We can simply rely on a Linux file system, look into /proc/CPU info and get that information from there, read it, suck it up into DPDK and start from there. Memory is also set up at this point. Since we use large buffer pools for packet processing, for every packet that is received, we also need to provide a free buffer back to the NIC for another packet to be stored in there. DPDK uses the traditional allocation mechanism of buffer pools, right? You just take a big amount of memory and you just chop it into fixed size slabs, and each slab will actually be able to store a packet. So that's why we are actually we need to spend a lot of attention on memory and getting the memory set up right. To avoid issues with TLB thrashing, we need to use huge pages. So that's a big topic to talk about. Probably we won't spend that much time on it right now. As Damian also said, VPP is using 1 gigabyte huge pages. This is actually a hardware feature of the CPU. You have to check with your CPU manufacturer whether this huge page feature is supported or not. On Intel CPUs, we do support 2 megabyte pages and 1 gigabyte pages in DPDK. So Why is that important? Because CPUs work with virtual addresses. Your program works with virtual addresses, but whenever you need to communicate with the I/O layer, the NIC actually uses physical addresses. So this translation needs to happen somewhere. So it happens in the CPU, it happens on the platform, and we actually have CPU side table looker side buffers, abbreviated TLBs. You have IO side TLBs to do all these translations. There are several translations involved into actually mapping a virtual address that your program uses to a physical address that your system is using. And this actually needs to happen fast, because on every packet you need to know this address. So the default page size of 4 kilobytes is actually not enough, not working properly with the right performance in this setup for packet processing, because one 4 kilobyte page will only allow you maybe to store 1 or 2 buffers, 1 or 2 packets in one page. So every, let's say, other packet, you would actually need to look to do this mapping again. So in order to avoid that, you need to minimize the number of pages that you use, so that you use fewer pages. You can store a cache of these page tables. So that's why we actually prefer to use 1 gigabyte huge pages. So then you could have a huge number of buffers in the same page. So you could have thousands, millions of buffers in just a few pages. So you don't need to keep a long list of these pages. So that's done by EAL as well. Also, the NICs are discovered at this point. So we just look on the PCI bus, look into the Linux file system to see which NICs do we have over there, where are they mapped to which CPU socket, and what's the proper driver that needs to handle those NICs. Of course, these NICs could be handled by the Linux kernel already, so we have to use the Linux standard mechanisms to actually remove that NIC from being handled by the Linux kernel and having it taken over by DPDK, right, and handled using the Polmo drivers that DPDK provides. So that's what EAL is doing really. It's just the setup, abstracting, providing a nice abstraction for the system, for the other libraries to use, right? So Mbuf is actually the packet descriptor. VPP uses this Mbuf as a packet descriptor. It also appends more data, more metadata to this data structure. I think DPDK Mbuf is 128 bytes, which is exactly 2 cache lines on Intel CPUs. And I think the VPP metadata that is appended to the Mbuf is 32 or 64 bytes.
I think Damian mentioned 2 cache lines.
Anyway, we can check in the code. I mean, it's not a big deal. I think there is a comment in the code about 32 bytes. I didn't count them myself. Maybe I should have done that. Anyway, so 32 or 64, that's another cache line, one more cache line that is part of, let's say, the core packet descriptor that VPP uses, that VPP graph nodes will have to share and all recognize. Mempool is the library implementing this pool of buffers, millions of buffers sometimes. For example, if you use traffic managers, you need to buffer a lot of packets for each output port, and you probably typically need millions of packets in a buffer pool to do that, depending on how many milliseconds of traffic, for example, you are planning to buffer for each output port. If you are not doing that, you might get away with a smaller mempool. I think what's the default in VPP? Is it 32 kilobytes of buffers in a memory pool? Okay, we can check. I think that's what we use in DPDK sample applications as a default. Ring is the library that provides support for lockless queues, lockless rings, lockless circular buffers. Why is it lockless? Because it's typically used for communication between several distinct threads that are running on different CPU cores. So basically, you have both of these threads running in parallel on different CPU cores, and they share the same data structure. A queue at the end of the day is just a buffer that is split into entries and handled using some indices. It's shared memory between these two threads running at the same time, as opposed to time sharing. So then they need to, we can either use semaphores, but we don't like to use semaphores for good reasons, because that involves blocking, and locking, which involves blocking, right? So we use lockless queues. It's actually very simple to implement a single producer, single consumer lockless queues. So easy to write the code. You can read the code. There are a few tricks in there, but at the end of the day, very small amount of code to do that. No special instructions, no special, let's say, hardware support needed there. Compare and swap is actually not needed for single producer, single consumer. If you want to implement multiple consumers, single producer, or single producer, multiple consumers, or multiple everything, then you would need to use some tricks. There is no easy way out. So typically you would use compare and swap instructions. But it's actually a good point. You don't need to use that for the simple case of single producer, single consumer. Okay, timer is obviously is there for implementing list of events that you need to trigger. For example, you need to age entries into a table, things like that. I actually am not a fan of using the timer library on the data plane side. So I'm okay to use it for, let's say, control plane stuff. But I usually find a workaround and a different way to do things when I need to implement a sort of timer events on the data plane threads, rather than actually relying on this thing, because actually stopping from time to time and actually parsing a linked list of entries is not a good thing. So usually a linked list is not a good thing for data plane processing, because a linked list means that you need to chase pointers. You need to you have a data dependency. You cannot go to the next. You need to parse it linearly. So if you have a lot of entries, there is no quicker way to do that. You have to parse it linearly. You cannot go 2 nodes at a time. You need to go 1 node first to actually get the pointer to the second node. So the dependency, the data dependency here is very strong. So don't use linked lists if you can. I actually had examples in DPDK where where we use arrays. If we can use arrays, sometimes you cannot use arrays. You need to use a linked list. So the workaround to do that is actually have a linked list where the nodes are actually arrays. So you have like a group of 4 entries that are in an array, and then they are linked to another group of 4 entries using a pointer. So basically it's a midway between a linked list and an array, just to avoid the huge penalty of
But if you need thousands of timers, protocol timers, what do you do?
Then you are in trouble. So the question is, do you need that for data plane or do you need that for control plane? If you need it for data plane, maybe you should think about writing your application in a different way, unless it's 30 years old code that nobody knows anymore. So you need to use this library. So that's like the set of core libraries. The next big thing is obviously the Polmo drivers. This is what DPDK is best known for. It's actually the driver providing you the packets. Read packets from the input queues of the NIC, write packets to the output queues of the NIC, packet in, packet out. And we have a huge set of devices over there of NICs, physical NICs, virtual NICs as well. So abstractions for, let's say, software devices, really. So Intel NICs, Mellanox, Broadcom, Cisco, and then all sorts of virtual devices like AF packet, rings, PCAP. We have a bonding driver as well. We also introduced these crypto devices, which are sort of Polmo drivers for accessing the queues of a hardware acceleration for encryption. We are not dealing with packets here, maybe, although you can create the connection to packets straight away. What really happens is you have a queue of requests, encryption or decryption requests, and a queue of responses back from the accelerator. So it's still a Polmo driver. You need to push requests and you need to poll for responses back. So that's why we have these crypto devices over there. We have support for the Intel Quick Assist technology. AES-NI multi-buffer is actually a software library using special Intel CPU instructions called AES-NI for AES encryption, algorithm symmetric encryption. NI stands for new instruction. So it's an instruction that is used basically to implement AES. And then we have this library that also pushes as many encryption decryption requests through the CPU execution units to achieve the maximum performance there. So what else? We do have these extensions, things that we call extensions to DPDK. We do have like classification libraries. Once you get your packets into the CPU, you need to obviously look them up into some tables. This is what we do all day long for packet processing. We look packets into tables to understand what to do next with the packets, what's the next table we need to look up that packet into. So we have hash libraries. We actually have several instantiations of those in DPDK that you could see. Some of them are more hidden than others. Hash is actually an exact match classification. You just need read your n tuple from the packet, a bunch of fields from the packet. You know exactly which bytes make up your classification key, your lookup key, and you look it up into a table just to get the data associated with that key. So it could actually be a pointer, an opaque index, which is like the typical usage that you see in VPP for that, or it could actually be an array of bytes, an array of bytes of data bytes associated with that key. It could be, it's actually metadata that you store for whatever, for that flow, for whatever that entry represents in your table. You have ACL lookup, access control list, so it's wildcard classification. You read your n tuple from the packet and you need to match that against a set of rules that are, for example, used in a security gateway. And you have like wildcards over there, and these rules will also overlap sometimes. Most of the times would actually overlap, and you will actually hit the same lookup key will actually hit several rules in that table. So how do you reconcile over that sort of event? You actually pick that rule that has the highest priority. So in a security gateway, in a firewall, you will actually see rules listed up in descending order, and the last rule, the lowest priority rule, will actually be drop everything. But then on the top, you have some other rules that will actually say, hey, accept this, deny this, send these packets over there, do this, do that. Yeah.
Are the rules sorted according to priority, so you don't have to scan to the end? The first match will always be the highest priority. Or does it have to scan to the end and then?
That's the way to look at it from the logical perspective. That's actually not the way it's implemented in the code. The data structures are actually a tree-like data structure, so you would it's very similar to implementing a pattern matching algorithm like AHOC or ASIC. You'll actually build a tree of things and you just go through that tree. The problem is on the performance side that each node in the tree is actually a memory access. So you need to kind of push more things in the same lookup. You need to minimize the number of memory accesses. So then you will actually not do one byte at a time. You will try to do as many bytes at a time in one node, in one access. I'm not the guy developing that library, so I actually cannot go too deep into that. But my understanding is that we are actually building a tree.
Tree traverse.
Yes, yes. But from a logical standpoint, if you just describe that to somebody, or you implement it in a naive way, you could actually do a for loop and just start parsing the rules and matching your key against the rules in descending priority order. And the first hit will actually win. LPM, longest prefix match, is used for typically for routing, for implementing a FIB, forwarding information base. So this is what VPP also implements. The algorithm is actually different. I think VPP uses an M3 to implement the FIB. We are not using an M3. We are using a different algorithm. We are very generous sometimes with memory. So our routing table would actually allow you to get to a resolution with just one memory access for most of the cases, where your prefix is actually of the route to hit is actually less or equal to 24 bits. So /1 to /24 you can actually do in one access. If your prefix is longer than that, then you might need a second access into memory.
Use the same data structure for V4 and V6? No. Do you use the same data structure for V6 and V4?
Is that working actually? Your mic is working?
I think it works.
Okay. So no. The short answer is no. So what happened historically is like we added a support for IPv4, and then at some point later we said, yeah, we should also add IPv6. So then we looked for various algorithms, and what happened is that we actually said, yeah, we can use the v6 version for the first 24 bits out of the IPv6 address. So then we extended it with some other tricks. So the V4 implementation is actually reused for V6, but there is a lot of other things that we need to add. The bad news is that it will take many more cycles than for V4 because it's more memory accesses, not just one.
Right. So VPP has different data structures as well. So the V6 uses a hash
yeah. At some point, I'll get to that and study that code as well. It's somewhere on the list. Too many things to do. So yeah, that's a good observation. So as we go along, I mean, we will borrow concepts from VPP. VPP will borrow concepts from DPDK. Will both improve. I mean, and will both evolve. Okay, extension libraries for packet distribution, like load balancing sort of thing. Packet reordering, like we mentioned yesterday, sometimes for an elephant flow, maybe the most elegant way to do that is to send packets from the same flow to different workers and then reorder. So we have a library for reordering over there, packet reordering. Yeah.
Do you think you can do 5-10 more minutes on this one and then switch to the other presentation?
Yes, that is exactly the plan.
Question to you, right? Yeah. Thank you. For this to parallelize the processing of elephant flows, do you need both the distributor and the reordering? To distribute to multiple worker threads, and then the reordering to collect and sort.
You could use both of them. Reordering is just one way, or distributor is just one way to load balance. You could actually use other schemes for load balancing as well, like RSS, which is a hardware scheme, flow director, hardware scheme, or maybe simple software implementations.
Yeah, but not for the elephant flow.
And not for the elephant flow, yes. So for the elephant flow, yeah, you're right. Sorry, I should think more about your question. So on the elephant flow, there is no purpose in computing using a hash or sort of digest per packet to bifurcate. You just send the next packet to the next worker that is available. So probably not the distributor.
But if you want to reorder the result, does the reorder?
Yeah, you simply assign sequence numbers to your packets, and then you reorder based on the sequence number.
Does that have to run on its own CPU, or can the reordering be invoked by the different worker threads? Because I've looked at the code, and I there is no mutual exclusion in the code. It's not obvious to see. Either you just put big locks around it, or you
I think I mean the idea with reorder is you reorder it. I mean, the only reason you need to reorder is because you have multiple threads involved,
Yes.
right? If you only have one thread, there is no need to reorder. So if reordering code would not be thread safe, then it would be meaningless.
But I don't think it's thread safe. So that's why I'm
I
wondering how it's supposed to be used.
I think it's one of the basic requirements, but I'm not that familiar with that library right now. I need to maybe spend more time looking into that. So we can maybe take it offline, right? And maybe I can better understand your requirement for your elephant flow use case and associated information. Yeah. IP fragmentation, IPv4, IPv6, IP reassembly, IPv4, IPv6 is present. Then quality of service for traffic metering and hierarchical scheduling on the egress side. We do have a library that to implement a 5-level hierarchical scheduler in software with actually no hardware acceleration. You can have thousands of queues as leaves of the hierarchy. I actually use this as an example for how to optimize code, how to write code optimally on one of the techniques that you could use to optimize code on multi-core CPUs. Packet framework is one of my babies as well. It actually provides a way to design your applications without worrying too much about moving packets from A to B. So typically, when you write your code, you just simply start with receive packets from that queue, then take the packet to the next table and do the lookup, and then you do if else's, whatever, you do branches over there just to, and then you move the packet to the next table, so on and so forth, and then you put packet into a queue or you drop the packet. So you will have to move the packet from A to B all the time. Packet framework, the philosophy comes from OpenFlow, which actually looks at a data plane of a switch as a chain or tree of tables that are connected together. So then the idea was, can we actually abstract all different types of devices that can stream packets, like hardware queues, software queues, IP fragmentation queues, IP reassembly queues, traffic managers. At the end of the day, they are just queues that would actually get packets on one side and send packets on the other side, maybe not in the same order, maybe with some kind of timeout. Maybe you get a lot of fragments in and you just send a single reassembled datagram out. But at the end of the day, it's still a queue. It might be a smart queue. And then you have all these tables that are just search algorithms. You just have whatever lookup keys, which are array of bytes, and you associate some data to these keys. So we put together all these devices that can stream packets under the port abstraction into the port library. We put together all the libraries that we have for lookups, ACL, hash, LPM, into this table abstraction library. And then we just, since they all look alike and you press the same button for all of them and they all sync, maybe in a different way, we can connect them together and you get for free this application skeleton. You just say, okay, this input port is connected to this table is connected to this other table. Then you just need to populate your tables with actions like, okay, for this, add these keys to the table, and for this entry in the table, do these things and send this packet over whatever next step. So you get, the idea is that you build all this skeleton for free. You get all this skeleton for free. It's built for you, and then you just need to call a function like run the pipeline, and the packets will seamlessly go through the pipeline without you having to write all this code all together all the time and maybe making mistake debugging your application. You get this for obviously. Packet framework is just a way. It's a methodology to connect these things together. VPP actually has a huge library of protocols that are already implemented, right? I mean, there is, if you look into the VNet folder of VPP, you'll see a huge list of protocols supported there. That's actually where the gold is. You won't find that in Packet Framework. Packet Framework is just a tool to change things up, but then you still need to implement your own protocols, right? We do have some examples for routing or flow classification, but it's just examples. We don't position those as a stack. VPP is the stack. If you need the stack, VPP is where you need to look. If you need to just write a simple application or a complex application from scratch, and you don't find, maybe, I mean, you have reasons not to use VPP, then you could use Packet Framework. Or maybe you could use both. I mean, there are actually people looking at using both together.